Today we will study about electric field due to a dipole at any point on the equatorial plane. Last day we studied electric field due to a dipole at any point on the axial line, but here it is equatorial plane. Let us consider the dipole minus q plus q charge separated by a vector distance 2l. Let C be the center of the dipole, then this distance BC will be L. Similarly, this distance AC also will be L. Let P be a point at a distance L from the center on the equatorial plane, and this particular plane is the equatorial plane, and this is not a line, it's a plane which is bisecting the length of the dipole at the center C. Now the point P is equidistant from minus charge as well as plus charge, and that distance should be x. Now at this point P, there is an electric field E plus due to positive charge, as well as there is an electric field E minus due to negative charge. This electric field is radially outwards because positive charge is creating the electric field, and this electric field is radially inwards because negative charge is creating the electric field. Now look at this electric field E plus, and that can be resolved in the y direction as well as x direction. Look at this electric field E minus, that also can be resolved in the y direction as well as x direction. This is theta angle, therefore this angle also will be theta, this angle also will be theta. Now E plus can be resolved in the y direction as E plus sine theta, as well as in the x direction E plus cos theta. E minus also can be resolved in the y direction E minus sine theta, as well as E minus cos theta along x direction. From this figure it is very clear that y components of electric field cancels out because they are equal and opposite. E plus sine theta cancels with E minus sine theta, while the x components get added up. X components get added up and act in the direction towards a negative charge of the dipole. Now what is the magnitude of E plus? The single charge E plus create an electric field at a distance x from it, and the magnitude of the E plus is given by 1 by 4 pi epsilon 0 q by x square, and the direction is in the direction AP. This is the direction of E plus. Similarly, the magnitude of E minus is given by 1 by 4 pi epsilon 0 q divided by x square, and the direction is PB. PB is the direction of E minus. The net electric field is given by E is equal to E plus cos theta plus E minus cos theta, because only cos components get added up, sine components cancels each other. Since E plus is equal to E minus, magnitude is 1 by 4 pi epsilon 0 q by x square. So E net electric field E can be written as 1 by 4 pi epsilon 0 q by x square cos theta plus 1 by 4 pi epsilon 0 q by x square cos theta. So that means 2 times 1 by 4 pi epsilon 0 q by x square cos theta. Put as equation number 3. Now I am going to substitute for cos theta. From this right angle triangle I can find out cos theta. From the right angle triangle, cos theta is equal to L by x. L by x. Put as equation number 4. If I am substituting 4 in 3, I will be getting E is equal to 2 into 1 by 4 pi epsilon 0 q by x square into L by x. So that means 2 into 1 by 4 pi epsilon 0 ql divided by x cube. Put as equation number 4. Now what is the next point is I want to substitute for x cube. From Pythagoras theorem, x is equal to x square is equal to r square r square plus l square. So this quantity is r, not l. So this quantity is r. The distance between the point P from the center of the dipole is r. Therefore x square is equal to r square plus l square, and therefore x is equal to r square plus l square all raised to 1 by 2. X cube is equal to x square into x. That means r square plus l square into r square plus l square all raised to 1 by 2. That will result r square plus l square all raised to 3 by 2. Put as equation number 5. Now I'm going to substitute equation number 5 in 4. So I will be getting E is equal to 1 by 4 pi epsilon 0 Q into 2L divided by R square plus L square all raised to 3 by 2. Now the previous assumption I am taking, L is very much lesser than R. Length of the dipole, half of the length of the dipole is much lesser than distance of the point from the center of the dipole. Therefore L cube can be neglected. When L cube is neglected, the resultant electric field can be written as E is equal to 1 by 4 pi epsilon 0 Q into 2L divided by, since L square term is neglected, not L cube term, L square term is neglected. Since L square term is neglected, it will be R square all raised to 3 by 2 only. R square all raised to 3 by 2 is nothing but R cube. Q into 2L can be written as P, the dipole moment vector. Therefore, the net electric field at any point on the equatorial plane can be written as E is equal to 1 by 4 pi epsilon 0 P divided by R cube into vector, unit vector R. So that means net electric field at any point on the equatorial plane can be calculated in this way. Now we yesterday studied electric field due to a dipole at axial line is 1 by 4 pi epsilon 0 2p divided by r cube. Today we studied electric field due to a dipole at equatorial plane is equal to 1 by 4 pi epsilon 0 p divided by r cube. Just to take the ratio, we will be getting EA divided by EE is equal to 2. So the ratio of electric field due to a dipole at any point on the axial line and that of equatorial plane is equal to 2. Now we are going to study the torque acting on an electric dipole placed in uniform electric field. You know what is uniform electric field? If electric field has the same magnitude and direction in a region, that electric field is called uniform electric field. Uniform electric field is represented by parallel lines, arrow-headed parallel lines. The arrowhead indicates the direction of electric field. Now I am going to place a dipole inside this uniform electric field. Minus q plus q charge separated by a vector distance 2L, that is a dipole. When the dipole is placed in electric field, both plus q charge and minus q charge experiences a force. When a charge is placed in electric field, it experiences a force QE, and if it is a positive charge, that force is in the direction of electric field. If it is a negative charge, that force is opposite to the electric field. So force acting on plus q charge, F plus is equal to QE. Force acting on minus q charge, F minus is equal to minus QE. Magnitude wise it is QE only. The negative sign indicates the direction. Therefore the net force is QE upwards, QE downwards. They should be added up together. Since the downwards force should be subtracted, QE minus QE, net force acting on the dipole is equal to 0. The meaning is, when the dipole is placed in uniform electric field, it experiences no net force. We already studied this is a condition for translational equilibrium. So that means if a dipole is placed in uniform electric field, it will not translate because no net force is acting on the body. But the line of action of these forces are different. This force is acting in this direction, this force is acting in this direction. They are not in the same line. Since the line of action is different, there exists a couple, and a couple causes rotation, and this dipole will rotate inside the electric field, and there exists a torque tau. And what is the magnitude of the torque? The magnitude of the torque is given by F into AB. The magnitude of the torque can be defined as a product of one of the force, magnitude of one of the force, and perpendicular distance between the forces. F is the magnitude of one of the force, that is QE, and AB is the perpendicular distance between the force. This force is acting in this direction and this force is acting in this direction. There is a perpendicular distance between these two forces, and that is what AB. Now we have to find out what is AB. From this right angle triangle, sin theta is equal to AB divided by 2L. AB divided by 2L sin theta. This is This is angle theta. From that equation, AB is equal to 12 into sine theta. Substituting this equation 2 and 3 in 1, I will be getting tau is equal to QE into 12 sine theta. Q into 12 can be written as P. We already studied dipole moment vector. Therefore, tau is equal to PE sine theta. In terms of vector notation, we can represent vector tau is equal to P cross E. Last year we studied cross product or vector product of two vectors. So this is the torque acting on an electric dipole when placed in an electric field. Now let us discuss various cases. Case number 1, theta is equal to 90 degree. So that means the dipole is placed perpendicular to the magnetic field, sorry, electric field. When the dipole is placed like this, perpendicular to the electric field, theta is equal to 90 degrees, sine of 90 is equal to 1, therefore tau is equal to PE maximum. The electric dipole experiences maximum torque when it is placed perpendicular to the magnetic field. Case number 2, theta is equal to 0. Theta is equal to 0 means electric dipole moment vector and electric field are in the same direction. That means the negative charge is placed here, positive charge is placed here in the same direction of electric field, so that electric dipole moment vector and electric field are in the same direction. Since theta is equal to 0, sin 0 is equal to 0, therefore tau is equal to PE into sin 0 is equal to 0, therefore tau is equal to PE. No torque act on the body. No torque act on the dipole. That means it is in equilibrium. This particular configuration is called stable equilibrium. Stable equilibrium is when positive charge is here and negative charge is here, so that dipole moment vector is in the direction of electric field. Now let us discuss case number 3. Theta is equal to 180 degrees, sine of 180 again 0. Here negative charge is placed here and positive charge is placed here, so dipole moment vector and electric field are opposite to each other. When the dipole moment vector and electric field are opposite to each other, theta is equal to 180 degree, sine 180 is equal to 0, therefore tau is equal to PE into sine 180, that also is equal to 0. And this particular configuration is called unstable equilibrium. So stable equilibrium is there when theta is equal to 0, and unstable equilibrium is where when theta is equal to 180 degree. Now one more question I want to discuss. What happens when a dipole is placed in non-uniform electric field? So we are discussing in uniform electric field only. In uniform electric field, force acting on plus q charge is equal to force acting on minus q charge, because charge remains same, electric field is also uniform. So if electric field is not uniform, for electric field at this point is not equal to electric field at this point, then the net force acting on the dipole will not be 0. Because this electric field is not equal to this electric field, there is an unbalanced force acting on the dipole. So when the dipole is placed in a non-uniform electric field, due to that unbalanced force, there exists a translatory motion also. Of course, there will be a rotatory motion, there will be a torque. In addition to that torque, there will be a translatory motion also, because a net force act on the dipole will not be 0. So answer for this question is, when the dipole is placed in non-uniform electric field, in addition to torque, the dipole experiences a net force, therefore there will be a translatory motion also.